Eğer ki hayatımızda hiç eğer olmasaydı nasıl olurdu? Size şöyle söyleyeyim. Her şey daha az parlak, daha az yeşil olurdu ve daha az parlak yeşil. Çünkü eğerler ormanların derinliklerinde tek bir kibritle derinlerin kıvılcımını ateşler. Eğerler Nobel ve Guggenheim'ın aklına takılır ve o kodu bu kodu çözerler. Eğerlerle içinizden haykırmak gelir. Eğerler bariyerleri kırarlar. Asla yalnız yürümezler ve aşırı bulaşıcıdırlar. Eğerler aşikardır ve son anda golü atarlar. Eğerler günü umursamazlar, robotlarla bile konuşabilirler. Karşı takım soluklanırken oynamaya durmadan devam ederler. Sadece basit bir kelime öyle mi? Hayır. Eğerler asla uyumazlar, hep daha fazla çaba gösterirler. Eğerler bakar, araştırır ve en beklenmedik zamanda ortaya çıkarlar. Eğerler klonlanarak çoğalırlar. Acaba gerçekten yapabilir misin? Yaptın bile. Eğerler aklınıza girmeye çalışan güler yüzlü şakacılardır. Eğerler kapıları açarlar, asla kaybetmeyeceklerini bilirler. Ve biraz gün ışığına her zaman hazırdırlar. Her şey bir eğerle başlar. Çünkü eğerler ne zamana dönüşür, ne zamanlarsa şimdi. Ve şimdi nasıla dönüşür. Nasılsa asıl. Eğerler bakış açınızı değiştirir. Eğerler oyunu değiştirir. Eğerler dünyayı değiştirir. Biliyoruz. Çünkü biz eğerlerle çalışıyoruz. Yakın Doğu Üniversitesi.
Okay, Münir presentation'ını yapacak. Tamam, yaptık. Her şey tamam. Beni duyuyor musunuz? Yes, I would like Professor Münir to present his keynote lecture, please. Thank you, Professor Münir.
You hear me? You hear me very well?
Yes, I can hear you.
Okay, and the screen is also
okay.
You can see it.
Okay,
right.
Good. Okay, yes.
Thank
upload
you.
it again, upload it.
Yes, yes. It's on, huh?
It's on, now it's on, yes.
Okay, thank you very much. So,
you're welcome.
Thank you. So, first of all, I'm thankful to Professor Chavit and Professor Safi for inviting me to deliver this keynote lecture as representing the African region. This work is a recent development, and I would mention that the content of the keynote talk is a bit different, is developed more than the file I sent you. So the presentation is titled "The New Tool for the Measurement of Soil's Shear Strength." Maybe it's modified. Okay. The outline of this work is introduction. So I will remind about soil testing method and what happens with the soil disturbance. Then I will present the novel tool called Cylindrical Penetrometer. Okay, and we will present the testing procedure. And using this tool, first investigation was on the determination of the unbrained cohesion of Tunis soft clay. And for this, we suggested a method of determination, and there was validation of the results by the cylindrical penetrometer results with the classical shear test. And as second investigation, so we will talk about the shear strength of cohesive frictional soil. And we will explain how we can determine the cohesion and the friction angle. And we will discuss, of course, the proposed results. And then conclusion and forthcoming development of this work. So when we deal with in situ soil testing method and related to disturbance, we can see on this slide, for example, in this first case on the left, when we do, for example, the pressure meter test, which needs to create a borehole, and the vertical, sides of this borehole are disturbed, and then we will introduce, or we will put our cell measurements, and as such, when we measure the called limit pressure, we measured in a disturbed soil, and this is, this is to say we are measuring failure characteristics affected by the disturbance of the soil prior to the measurement of shear phase. On the contrary, for example, we remind about the CPT or the SPT test. Okay, so we have the tool which placed at the bottom of the boring, and then we, for preparing to the test, we have an initial penetration without measurements, and after that we will push, or the tool penetrates the soil to measure the tip resistance or the end blow count. So that means we can distinguish between, for example, the pressure meter test and the other test. We have soil affected by the disturbance prior to the measurements. And in this case, we can say that the failure characteristics are not affected by the soil disturbance. So, but is methodology of determination. So we need to estimate failure characteristics, the well-known cohesion and friction angle. And all time from those in situ tests, SPT, CPT, or pressure meter, we usually need correlation. That means we will measure, for example, the end blow count, or we measure the tip resistance, or we will measure the limit net pressure, and using correlation, we will deduce either the friction angle or maybe the end-to-end cohesion, etc. So this means I can say that we have a main limitation when estimating failure characteristics, because we will use correlation, and we know that correlation depends on the soil type and location, and we can say that it is not accurate for the design. But I can add also, it is non-direct determination of C and phi. That means from the classical in situ test, we cannot measure directly the cohesion and friction angle. And in the same context, when we deal with soft soil, we have disturbance. So we know that prior to the in situ test or prior to the laboratory test, the occurrence of a disturbance is more likely. And for example, to reduce the disturbance effect from soft soil, there is the vein shear test, which enables to reduce the disturbance before the measurement of the SU. But with a device or apparatus, we still face the overestimation of the end-to-end cohesion. And using the same methodology, we have to introduce correction factor and correlation, which not always applicable or applicable with restriction depending on the soft soil we are considering. We suggested earlier for the vein shear test to limit the measurements of the torque in the range of small deformation. And we suggested the method to determine maybe safely the end-grained cohesion, to not overestimate these characteristics, but still the disturbance effect is not solved. This means using the vein shear test or performing the vein shear test when you penetrate the soil before the measurements, the blade of the vein apparatus. So we have some disturbance of the soil, and as such came the idea how to think about a new tool or new method of measurements to avoid the disturbance effect and also to provide a direct determination of the cohesion and the friction angle for all soil types without using correlation. And this is the main purpose. And the first idea came in 2013 for the issue measurements because in our laboratory we investigate very much the behavior of Tunis soft clay, characterization, etc., using different experiments and numerical approach, etc. And the first investigation concerned the Tunis soft clay. We know a soft soil, its characterization informed that it has low permeability, colloidal and compressible structure, and the end-grained shear resistance is reduced to end-grained cohesion. The soil is purely cohesive. And but when sampling in soft clay, we have the soil disturbance, and again we have unreliable determination of the end-grained cohesion. So the tool we are suggesting, first we call it the cylindrical shear tool, but later or recently we changed the cylindrical penetrometer. So what are the components of the tool? We can see here that this is the tool, and it's composed by a hollow cylinder, 2, and a piston. Piston is part 3, is this upper side. And then the piston itself comprises 2 components, an annular ring, 4, and a headless socket screw, 5. Okay. And the annular ring itself comprises an inferior disc, 6, the lower part, and a superior disc, 7, which we can see here. So the design of the cylindrical penetrometer was possible by manufacturing 2 sizes. We call the small size, which is on the right, and the big size, which is on the left. And here we have the dimension of the cylindrical penetrometer. So with the big size, the height is 100 millimeters, and internal diameter, inner diameter, about 60 millimeters, and the small size, the height is 70 millimeters, and the inner diameter is 35.2. Okay, so how it works? The cylindrical penetrometer is a shear tool, and we can say it's a thin hollow cylinder with a sharpened tip. It means at the lower part here, we have a sharpened tip of this cylindrical penetrometer. So we need, after preparing a soil sample, we need to position the tool. And on the slide, so sometimes you will see CST, the first name we gave it to the SIP. Sometimes you will see the CP, but it's the same thing. So we need to position the tool at the upper side of the soil sample, and then similar to the SPT test, we will make an initial penetration without measurements. That means we will have a downward displacement of the tool, and we have an initial penetration D0. Okay, and then we will start the shear phase. That is the penetration of the CP or the CST over a penetration going from D0, the initial penetration, to the final one, DF. So it works like a penetrometer, but without a tip. There is no tip. You only have the shaft component. First investigation was about using reconstituted Tunis soft clay. On this picture, you can see a consolidation cell in which we reconstitute the soft clay with height 45 centimeter and near diameter 90, and the soil was consolidated under 30 kPa. And after the initial consolidation, the present study, as we can see here, we have many parameters to characterize the reconstituted soft clay. For example, total unit weight is about 70, water content about 51, and so on, specific gravity, liquid limit, etc. But we compared this reconstituted soil with the prior work since 20 years. In the prior work, we can see that the reconstituted soil have a similar total unit weight and similar water content, maybe slightly different parameters about the liquid limit plasticity index, but overall it's soft soil. And we can see here that for the earlier work, the undrained cohesion was 8 kPa and quite negligible undrained friction angle. And in the recent work, we collected so many data about Tunis soft clay. Here we can see many locations in the Tunis city, and we have had a lot of projects, and you can see that mostly Tunis soft clay is in the range of plastic to highly plastic clays, fully organic, not very organic. And here we can see the present study. So here we have the data of the reconstituted soil. We take it somewhere in Tunis. Now, after reconstitution in this consolidation cell, we say cut it in 3 portions, each of 15 centimeter thickness. And we have portion 1, portion 2, and portion 3. So we will show the location of the test we performed using the cylindrical penetrometer on a side of a sample portion. We will understand maybe easier. So as we can see here, for example, if I will take portion 2, at the upper side, I will do, I can do a test using the big size tool and 2 tests using the small size tool. Of course, respecting some minimum distance from the border of the cell where we reconstitute the soil. And as we can see here, when we cut the 3 portion, we performed the test using the big size tool at the upper side of portion 2, at the bottom side, and equally for portion 3 at the upper side and the bottom side. Why? Using the small tool, we performed 2 other tests as explained here. So that means in total we performed about 4 plus 4, 8, and plus 4, 12 tests. While for portion 1 we didn't consider it for the cylindrical penetrometer testing. In details, so we use for testing the triaxial load frame, as we can see here, and the soil sample is there, 1, okay, and the load frame is here, and we use a load cell to measure the resistance of the soil when, of course, the tool penetrates the soft soil, And here we have a displacement transducer to measure the penetration. And the rate of penetration corresponds roughly to the unbrained condition. It's, say, a speedy test in terms of rate of penetration. Now, this is what we performed for the test, but how we will determine the SU? First of all, we can say that in terms of shear strain developed during the direct shear test and the cylindrical shear tool, or the CP, cylindrical penetrometer, there is some similarity. But the difference, the main difference is the following, that when we perform the direct shear test, we have soil-to-soil failure. But when we perform the cylindrical shear tool, we have a soil tool failure, or CST failure. That means we measure the interface characteristics. But first of all, we can, for a given penetration, we can calculate the sheared area by the penetrated tool. That is both the shaft perimeter multiplied by this penetration for from inside and outside. So this is the total sheared area. But we know, as we so in the stable friction angle of purely cohesive soil is mostly zero, and the shear strength reduces to the unbrained cohesion. So here an example of the measurements of the load penetration curve using the CP. And of course, if we can imagine what we'll obtain, the more you penetrate, or the tool penetrates the soft soil, the more the resistance is increasing. And that means at some stage we never saw a peak for the load penetration curve. But the problem is where we should get the ultimate force and the corresponding ultimate penetration to determine the SU. This is the question. So, and here we are again, we need to remind that determining failure characteristics should be all time in small deformation. Okay, and as we can see here, for this case, the penetration is about 1 centimeters to determine the ultimate vertical force. So the SU simply can be determined from this equation, saying that the total force, resisting force to the penetration of the tool, is the SU value, which is considered constant. We have small penetration, multiplied by the total contact area between the soil and the tool. And of course, after performing all the tests I showed you, we in this table we can see, for example, the data we collected from all the tests. So in this, we have from the CP test, we ultimate penetration and the ultimate force, and the calculated SU CST, that means the unbrained cohesion from the cylindrical shear test or the cylindrical penetrometer. And we can see that those values are quite small. Now, we determine the average value, for example, portion of the reconstituted, sometimes using the big size tool and the small tool. Okay, and we will be again, the comparison. And as we can see here, the average value using portion is about 9.4. While for the example here, we have 12.5. And in the third part, upper side, 9.2. But we can say that in total average for the SU determined by the SU CST is about 9.8. We compared those values direct shear test performed on the same reconstituted soil, and it was the sample which is at the upper side, where we did not perform the cylindrical penetrometer test. And as we can see here, there is a good match between the unbrained cohesion determined by the direct shear test and the CST test. But of course, there is some relative difference depending on the case. So we can see here that the relative difference is quite small, very small, and the ratio between the two waves is roughly 1. Only in this case, maybe we have regarding this this ratio, if this ratio is lower than 1, that means the SU measured by the CST is lower than the one measured by the direct shear test. But overall, in terms of average value, we are not, I will not say we are close, depending on the case, but we are in the same range of the determined unbrained cohesion. And as for the purpose of comparison, to assess the CP test results for tuned soft clay, in an earlier work, we performed unbrained pre-axle test, but on consolidated samples. It's like consolidated unbrained. And as we can see here, of course, the more we consolidate, the more the SU, which reduces to the failure resistance, increases a bit. But here we can see we have the data for the test we performed under 30 kPa. And second, considering the shear, direct shear test SU envelope from different tests, so we can say that we can measure accurately the unbrained cohesion of a soft soil using the CP tool as compared to the classical triaxial shear test. Now, of course, in our thinking, it is possible to measure the unbrained cohesion. It's maybe simpler than the cohesion of frictional soils. And as continuation of the first investigation, we can ask this question: is it possible using the CP to measure the friction angle of a purely frictional soil? The reply is yes, but don't forget that the mobilized friction angle along the CP is rather the interface soil CP friction angle, the well-known delta F. That means the friction angle of the interface between a soil and, say, some rigid medium. Second question, if we can determine the friction angle, but we can say, can we determine the shear strength of the interface soil CP friction angle and the cohesion as well? That means our soil is both cohesive and frictional. Okay, the reply is yes, but how to proceed? So, and now this is maybe the part of the presentation which is not included in the paper I submitted to the ZM conference. So, in terms of experimental investigation, so we took a curry sand, usually used for construction, and we determined the grind size distribution of the sand. It is likely well-graded sand with the specific gravity 2.643. And as it is a loose sand from the direct shear test, we measured about 29 degrees friction angle and 0 cohesion. Okay, and then we performed, say, 2 states of reference. That means we will compact the sand, both in normal Proctor condition and modified Proctor condition. Of course, we need to determine the optimal water content for the 2 compacted or 2 state of reference, as of course, as we can see here, for the normal Proctor test, the maximum dry density is a bit low, 18, but for the modified Proctor test is rather 18.5. and the water content is a bit lower, say 10.5 or 8.5 for the modified Proctor. Okay, so using the Proctor specimen, compact Proctor specimen, we performed the direct shear test, and we measured for the sand. When it is the case of remolded dry sand, the cohesion is about 2.6 and the friction angle is 33. And for the compacted sand at the optimum Proctor water content, the cohesion is a bit higher, and also the friction angle is about 39 degrees, maybe a little bit. What does it mean? It means that the compaction induced a non-negligible cohesion of this supposed or assumed cohesionless soil when it is naturally deposited. So this means we have an idea about the cohesion and friction angle of the sand in the two reference state. Now, using or performing the CP test on those compacted sand at optimum water content, this is what we obtain in terms of recorded vertical force in Newton and the penetration of the CP. Okay, we can see that we have like a cloud of dots, and the average trends can be written under this form. That means because we have like fluctuation when measuring the, I didn't show you the load displacement curve, I mean, during the test, but we have some fluctuation, okay? But we can say that the ultimate load is proportional to the ultimate penetration. But the problem is, as we mentioned for the soft clay, we have an increasing force. Which couple do we have to take as ultimate force and the corresponding ultimate penetration to consider for determining the failure characteristics? This is the problem. And then here we move to the method of determination we are suggesting. So let us start first. The soil is assumed cohesionless. That means cohesion is zero. And we know that the shaft component or the tangential component or the shear stress is the normal stress, that is the horizontal one, multiplying the tangent delta F. Okay? And as we can see here, we add Kp, the coefficient of passive earth pressure. Why? Because when the CP penetrate the soil, it displaces it toward the soil. That the soil is rather in passive state because the CP, the cylindrical penetrometer, move toward the soil. And as such, we can calculate the ultimate force by integrating between the initial penetration and the final one using this equation. And what we obtain, we can rearrange this equation as follows. Here we have only a function of the friction angle. Delta F is mostly proportional to the friction angle, and the coefficient of proportionality may be from 0.5 to 1. And the Kp, considering the Rankine theory, is maybe the ratio between 1 plus sinus phi and 1 minus sinus phi. And on the right side, we have a function where we have known parameters or value. We know that the ultimate force we can measure, as well as the ultimate one, and gamma and the internal and the external diameter of the CP are known. So what is the method of determination? In a first simplified approach, we considered a fully mobilized friction. That means I can assume that the delta F is equal phi. That means alpha equal 1. And then we can say that we have an analytical function which only depends on the friction angle, and an experimental function which depends on the vertical force and the penetration of the tool. And we need to look for the value of the friction angle which fits the balance between the experimental function and the analytical function. And of course, we have to run maybe calculation, but targeting the friction angle in this range, because we know we measured for the sand about 28 degrees loose sand, and when well compacted, it is almost by 40 degrees. But we considered very small increment when we are changing the friction angle. And now what we can see here, of course, when calculating the experimental function, we need to take the value of P ultimate and D ultimate. And this equation comes from the observed one. I didn't mention it's the 2 or 3 slides previous one. And what we will do, we will vary the ultimate penetration and the vertical force that we use to calculate the experimental function, and along with variation of the friction angle to calculate the analytical function. And of course, we need to use Excel solver, and for example, to look for the phi value considering the relative difference between the experimental function and the analytical function in terms of percentage that is quite small. For example, maybe I will show you the Excel sheet later. So if I assume cohesion is 0 and I neglect the weight of the cylindrical penetrometer, we determined about 39.4 degrees as value of the friction angle. And this value is a bit overestimated regarding what we measured in terms of the shear strength, in terms of the direct shear test. So the idea is, so the way we are thinking, the way we are doing will help us. So now we need to take account of the cohesion and investigate the case of a cohesive and frictional. Of course, briefly, what can we say? The failure stress in terms of shear stress is C plus horizontal stress tangent delta phi. And the balance of forces when performed with the CP test, I cannot go through details. We can write P ultimate minus the weight of the cylindrical penetrometer is equal to this quantity. Okay. And for example, using the small size tool, the weight is about 1.46 Newton. And then now the expression of the analytical function remains the same, but the one of the experiment is changing. Why? Because we have the cohesion component. And now what I can do, for example, after the direct shear test, we measured cohesion about 5, and the friction angle was about 38. And I will show you right now on the Excel sheet that we obtained a very similar value using this method of resolution. Okay, so now to conclude about this work, we suggest a novel tool for shear strength determination, which is called the cylindrical penetrometer. The merit of this tool is to avoid soil dispersions and the use of correlation at the same time. From experiment, we did experiments by manufacturing two cylindrical penetrometer models, and we considered first the constitution of two soft clay, and we performed some tests. It's not only determination of SU, but we suggest a novel method of determination of SU specific to cylindrical penetrometer, and the measured and drained cohesion is found somehow dependent of the CST model diameter. I mean, using the small size or the big size tool, we determine quite similar SU value. And the assessment of the CP test results for soft clay was after comparison with direct shear and triaxial shear test results. And the recommendation, of course, is to do more tests for other, maybe soft soils, etc. Now, the second part of the conclusion, regarding the cohesive frictional soil, so we can determine the friction angle and the cohesion, but the method assumes a presumed soil cohesion, and the friction angle is can be determined accurately. And the assessment of CP results with direct shear test is promising. So after the Excel sheet calculation I am suggesting. So for common development, using the CP for testing intact soil specimen that we collect from geotechnical investigation, in situ geotechnical investigation. So we started already this work. And the CP, as I hope you understood clearly, but the CP is a model of Shelby tube, what we usually use to collect samples. But in situ investigation so is very feasible using this tool, and it is programmed to use the cylindrical penetrometer to determine the cohesion friction angle using an in situ test, say in full scale condition. So about publication, because it's recent work. So 2021 we have had a paper on the Third Asian Conference Physical Modeling Geotechniques, and we patented this this tool at the national level in Tunisia, and we submitted the PCT. Let me tell you that for the national one, it is agreed, but for the PCT, the reviewers say that it's not original work, but yet we did not respond to them. And also in the very recent Sydney conference, we suggested paper, and at this stage, more importantly, we submitted a paper in the Geotechnical Testing Journal, ISTM, and we submitted the revised version. More likely it will be accepted. So acknowledgement goes to Mr. Dalal Azaiz, my PhD students. She manufactured the 2 CP model and performed the CP test by herself. And later, or recently, Mr. Sergio Andromaniavi and other PhD students will participate with us to perform the forthcoming developments. Also, of course, for CP expenses, manufacturing, and so on, Sempro Tunisia Consulting is acknowledged to support this research investigation. And thank you very much for your attention.
Munir, thank you very much for your perfect keynote. Is Ivan there, please? Because I'm going to speak on behalf of Ivan. Yes, okay. On behalf of Ivan, which he can see you, and actually you can see your picture. We can hear your voice. We can see Ivan. We cannot hear his voice. So I am trying to communicate like that. And I would like to thank, as I said, on behalf of Ivan, and I will thank Ivan for accepting our invitation to chair this section, and also Professor Munir. We are as organizers of this conference, the Turkish Soil Mechanics and Geotechnical Society and Nearest University. We are thankful to you for accepting our invitation and delivering this perfect keynote. I would like to declare this session closed, and we are going to open the session 4 of the afternoon section in a few minutes. Thank you very much. Thank you all. Bir reklam arası koyabilirsiniz.
I'm catching a bus. Never nothing when it's real, yeah, it does. I'm flying above. No bluffing, no worry, keep it coming, yeah, I can say it's something. Simply what you gotta go. Can you feel the rush? So let's go. Feel the rush, adrenaline running through us.
I'll see you soon. How many we have? How many joined us? Can we put them on the screen, please? Katılanları görebilir miyiz? Katılan kaç kişi katıldı? Necan hoş geldin. Nil hoş geldin.
Merhabalar.
Merhabalar hocam, nasılsınız?
Merhabalar.
Merhaba Nil hocam.
Merhaba,
Böyle
merhabalar Necan
Güler
hocam.
yüzleri görmek ne güzel.
Sağ olun.
Peter, welcome.
Hello.
Sorry.
Merhaba hocam.
Peter hoş geldin.
Hoş bulduk hocam.
Evet, Selçuk'a yazıyorduk. Birinci yazar Selçuk ya. Because Selçuk was the first. We were sending him the emails because the assistants made a mistake. You are the presenter. They should have sent it to you. But
Yeah, I understood.
this time I think
understand.
we sent it not to you.
Mhm.
Kyun Ho Park.
Yes, speaking.
Nice to see you.
Thank
You
you.
are
Nice to see
joining
you.
us. You are joining us. What's the time in your country now?
I live in Trinidad.
I know you live in Trinidad. What's the time now?
Yeah. Here,
The
I
time.
stay in Korea now. My time is 7
You are in Korea
p.m.
now.
Yes, 7
So
p.m.
I know in Korea.
Yeah.
Yes, yes, is pity. I know Korea very well. I went 5 times to Korea.
Oh, that's good.
Yeah, Professor Shin is my dear friend.
Oh, that's great.
Yes. Want to go? Oh, we cannot see you. Can we see you? And Yan Li as well. Can we see you?
Hi, Professor.
Yan Li. Nice
Hi,
to see you.
Professor. Nice to meet you. Nice to meet you.
Yes, you are joining us from.
Yeah, I'm from Japan. Join us. Join you.
I know from Japan. Is Japan only 1 hour? So you are in Japan now. You are 7 hours from us. We are
Yes.
13:31.
Now it's 7:30.
Is
7:30 p.m.
is 7:30. So only 6 hours, like
Yes, only 6
Korea.
hours. Yes.
Yeah. Okay. I got a Japanese car, and my car, it doesn't change the clock, so I don't know. I thought maybe 1 hour, but it's okay. I've been to Okinawa before just pandemic. One, can we see you? Because what we did yesterday, I wanted to take a picture, and some of them left. So maybe dear session chair, at the beginning we'll take a picture, I thought, but one is not there. We cannot hear you. Your microphone is not on, one.
Professor Atalar, we have one more presentation. Are they here? Petra Ola
Dear
and
session
Peter Görek.
one. Yeah.
Cavit Hocam, Von bizim co-author, beraber paper. Belki o yüzden şey mi yapıyor acaba dedim. Oradan mı izliyor?
Okay. Sen alabilir misin bir fotoğraf Necan?
Tabii hocam, alayım. Okay, smile, we will take a picture. Okay, I got the picture, thank you. Professor Atalar, we have one more presentation. Welcome, Professor Barbasu.
Hello. Okay, wait for Michael. Michael, I'm not quite sure, but it's maybe midnight.
I'm sorry?
Professor Michael.
Yeah. I can hear you well. Can you hear me?
Yes.
Okay.
And Yasin as well. Welcome, Yasin. From Boğaziçi University or Earthquake Engineering.
Yes, Professor, that's right. Yeah, from Boğaziçi University, Kandil Observatory and Earthquake Research Institute.
But we are missing one of the speakers, is that right? There is one presentation missing.
It may be joined later.
Okay.
Michael, nice to see you. You were here yesterday morning as well. What's the time where you are?
Well, yesterday I was traveling. I was coming from US because originally I had a ticket plane to come to Cyprus. And then I stopped in Europe because I have another conference in Europe early next week. Yeah. So now I'm in Europe, but yesterday I was on the 2 zones.
Okay. And now, where are you now?
Actually, right now I'm in Romania. I'm going to Austria tomorrow.
Sorry, we didn't get it.
I'm in Romania because I had the ticket from Romania to Istanbul originally, and I'll fly to Austria tomorrow.
Okay, good. Nejan, can we take a picture?
Tabii, yes, I will take a picture. Okay, if everyone can look at the screen, thank you. I took a picture, thanks.
Okay. I would like all of you to thank you for your contribution to our conference. And I would like Professor Nejan for accepting our invitation to chair this session as well. And of course, Nejan is a member of the management committee of the Turkish Society of Soil Mechanics and Geotechnical Engineering, which we are organizing the conference together with Nearest University, and I am in Nearest University now. Yesterday, the conference jointly was gone through together with Professor Feyza Çinicioğlu and me in Lefkoşa. So, and now Necan, she's in Ankara, and I will give the stage to say, although it's an online stage, to Necan. If possible, dear session chair, if we can have the sessions about 10 minutes to catch up the half an hour or to go on time.
Okay.
Thank you all.
Okay. Thank you, hocam. Thank you,
Teşekkürler. Thank you.
everyone, for joining.
We took the picture, didn't we?
Yes, I got the
The
pictures. I
picture
will
is
send you.
taken.
Yes.
Thank you. Well done.
Okay, so when they start, we will start. Each one of you presenters will have
You are
about
going to
10.
start.
Okay, we will have 10 minutes for each presenter. Then I will try to give a comment or one question to each one of you, or just a comment. Then we will go to the next speaker. There is no question and answer session live. Thank you all for your presentations. Whenever you are ready, hocam, we are ready.
We are ready. I think we are ready. Just checking with the technical service. Okay, we are ready. You can carry on because it's live.
Okay. Did we start already broadcasting?
We are on. Yes, we are
Oh,
on.
okay. Okay, sorry. Welcome everyone to the session in the afternoon. This session will be about stability of slopes and landslides. We have a variety of different presentations. I would like to thank to all the attendees and all the presenters. The first speaker will be Dr. Mr. Park from Korea. The topic is numerical analysis of slope instability due to water pipe leakage. We are ready to listen to you, Mr. Park. You can share your screen.
Okay, then how can I upload my presentation file?
In the bottom part, there is a share button. Do you see there is a plus sign and share button? You can share your screen.
Plus sign.
In the lower part of the screen, you will see share.
Sorry, I cannot see the share button. Is the setting or where?
In the lower part, next to the setting, there should be a share option. No, you don't see that?
There's, oh, sorry. I can see only mic, camera, setting, chat, and leave.
Okay, then our technical colleagues, maybe you didn't give permission to share or something. Mr. Park cannot see the share button. Is it possible to? Okay, we will wait 1 minute. They are checking the options.
Okay, thank you.
Okay. Is it possible now? Let's check with our technical staff. Yes, they are asking you to send the presentation.
My presentation file.
Okay. Do you see in the chat they have typed an email address? Is it possible?
Oh, sorry. Now, I cannot look at my chat also.
Okay.
I don't know what's happening.
Okay.
Oh, now in the chat.
Yes.
Here to send the presentation file to there.
Yes. Sorry for the delay, dear audience. It will take just a few minutes.
Let me see.
Okay, is it possible to send your presentation?
Let's see, I'm sending now. Yes. Oh. GLU and UTTT. I think I sent.
Okay. Okay, so presentation is now sent by email. The technical staff will check the email. Sorry for this technical problem. We will soon start the presentations. Okay. Thank you to all participants. I think we have been listening to interesting talks, keynote lectures, and yesterday in other sessions, there were interesting presentations. Thank you to all participants in the conference. We would like to also thank Professor Javit Atalar for this conference. He has been very busy with the preparations, but I hope everything is fine and everybody enjoys the conference. We had a variety of different countries participating in the conference today as well in this session. Yesterday also we had colleagues from all around the world. Thank you to everyone for joining us. I'm joining from Ankara, Turkey, and Professor Javit Atalar is in the northern Cyprus. Okay. Okay, presentation has not arrived in the email yet. Was the file big? File size big, Dr. Park? Maybe didn't reach to the email address yet. Okay. Okay, we need just 1 more minute. Sorry for this delay. If anybody wants to get coffee and tea, in normal conferences face-to-face, we would have these coffee breaks to chat. If you want to grab a tea or coffee, we will need 1 or 2 more minutes. Okay.
Yes, now I think got it. Go, yes.
Okay.
Send by Park, yes.
Okay. We will be checking the presentation soon.
Yes, 2 times. Yes, this will be successful now.
Okay.
Hopefully.
Yes, the presentation is now ready.
Oh, ready.
Okay. Sorry for this technical difficulty. Mr. Park, you can start your presentation.
Thank you very much for preparation. Hello, everyone. My name is Kyung-ho Park. Today, I want to talk about the slope failures in Trinidad. Shall we go next slide? Next slide, yes. Trinidad is a tropical island located at the south fringe of the Caribbean Sea. The area is approximately 4,800 square kilometers, and the climate is seasonal with a dry season from January through May and the wet season from June through December. The average annual rainfall is around 1,500 millimeters. Next slide. Topographically, the island is divided by 3 mountain ranges, separated by undulating land, plains, and swamps. The northern range the central range, and the southern range. Landslides are commonly occur through all the mountain ranges. Especially in the southern ranges, landslides have been occurred along the traffic road. If the road is destroyed, a car cannot pass through it, it will have a significant impact on the lives of the local residents. Today's story is about the road slope failures that occurred in Chatham village of the southern Trinidad. As you can see in this slide, two slides, landslide A and landslide B, occurred. Today, I will focus on the landslide B. Next slide, please. This slide shows a scene from landslide A. It was a two-lane road, but one lane was failed, so the traffic is only passing through the remaining lane. Note that 400 millimeter diameter water pipe is exposed on the right side. Next slide, please. This slide shows the landslide B scene. It is about 10 meters away from the landslide A. Next slide, please. This slide shows landslide B scene in more detail. Again, slope failure occurred on one of the two road lanes, and so the traffic is only passing through the remaining lane. If you think the size of this slope failure is small, then how about the next slide? Next slide, please. This slide shows the slope failures occurred in 2018 in Bamboo Village of southern Trinidad. The height of the failed slope is about 25 to 30 meters. And as you can see in photo, the road as well as 5 houses were completely destroyed. Next slide, please. Then, the one question arises. What caused these slope failures? First, it is not rain, which is the most common trigger of the slope failures around the world. There was no record of the rainfall before and during the slope failures. By the way, the local residents claimed that they saw the leakage of the water pipe, and they believed that the slope failures were caused by a leak in water pipe. Could a water pipe leakage be the cause of these slope failures? This study was started to find an answer to these questions. Next slide, please. For the methodology, first, we collected geotechnical investigation report from the local companies. The EISL, a local company, conducted this landslide investigation in 2016. From the EISL landslide investigation report, a typical cross-section for landslide B was obtained as shown in this slide, and the information on the soil condition of the slope was summarized in this table. There are two soil layers. The surface layer is a clay layer classified as CH by Unified soil classification system, and below it, a clay layer classified as SC, sand clay, and the plasticity index values are 45 and 23 for layer 1 and layer 2 respectively. And then numerical analysis was conducted in two ways. First, unsaturated flow analysis was conducted by using CW software to obtain the water pressure distribution. And then the slope stability analysis was conducted using slope W software to calculate the factor of safety during the water leakage. Next slide, please. For unsaturated flow analysis, the soil water characteristic curve is required. Since there is no experimental data on this, the functional parameter regression model was used in this study. First, the parameter values were obtained by using the plasticity index values from the EIS report and the regression model as shown in this equation. And then the soil water characteristic curve for first layer and the second layer were obtained by using the purulent and thin SWCC equation as shown in this figure. And next slide, please. And this slide shows a typical modeling mesh in this study. One of the important factors in this numerical study is how to model the water leakage. In this study, the flow rate was used. The flow rate was varied from 10 to the minus 7 to 10 to the minus 6 cubic meter per sec at the location of the pipe, which is expected to leaking the water. Next slide, please. Then result and discussion. This slide shows the result of factor of safety for different flow rate with respect to the time, the duration of 180 days, 6 months. For the flow rate of the 10 to the minus 6 cubic meter per sec, as you can see in the solid line, the factor of safety fell below 1 at the time of 9 days. For the flow rate of 5 times 10 to the minus 7 cubic meter per sec, the factor of safety fell below 1 at the time of 57 days. For the flow rate of 2 times 10 to the minus 7 and 10 to the minus 7 cubic meter per sec, the factor of safety keeps above 1 for 180 days, and so no failure is expected. From this result, we can see the flow rate is one of the important factors that can be considered in the slope stability analysis. The next slide, please. This slide shows the result of the water pressure distribution for different flow rate. For the flow rate of the 10 to the minus 6 cubic meter per sec, and at the time of the 9 days, the factor of safety fell below 1, and for the pressure distribution around the 5 is about 240 to 260 kPa. For the flow rate of the 5 times 10 to the minus 7 cubic meter per sec, and at the time of the 57 days, factor of safety very below 1, and the water pressure around the 5 is about 120 to 140 kPa. So we expect that the higher flow rate result in higher water pressure within a shorter time and increasing the likelihood of the slope failures. Next slide, please. For the flow rate of the 2 times 10 to the minus 7 and 10 to the minus 7 cubic meter per sec, and at the time of 180 days, the water pressure around the 5 is about 20 to 60 kPa, so it's lower than other cases. Next slide, please. Finally, the following conclusion can be drawn in this study. First, the water pipe leakage can result in slope instability, and the rate of the leakage is an important factor that should be considered in slope stability analysis. Second, higher flow rate results in higher water pressure around the pipe within a shorter time, increasing the likelihood of the slope failures. Thus, it is important to repair the damages to linking buried water pipe early and before it becomes worse. This is all my presentation, and thank you very much for your attention. Thank you.
Thank you, Mr. Park, for your presentation. Interesting issue about slope stability and pipe leakage. I was wondering if the depth of the failure surface is known, the zone of failure surface. Because what I was thinking is the landslide may have caused the pipe to be damaged and leak. Could that be an option or no?
Oh, that was also possible. It's really good question. I also thinking about that, but still, I cannot clear answer for that.
Okay.
But that
Thank
is
you very
also
much.
happen in the some certain area in the Trinidad.
Okay.
And will
Thank
I
you very
continue
much.
for that also? Thank you.
All right. Thank you. Now we will be going to the next presentation. Let me check the schedule. The next presentation is about uplift-induced levee failure in a centrifuge test. Girardi will be presenting. Girardi et al. Oh, sorry. I was looking at the wrong session. I'm sorry about this. Yes, where is the... Sorry about that. The next presentation will be Ms. Nil Kutlu. It's about unsupported vertical cuts. Welcome, Ms. Kutlu.
Thank you very much.
Before you start, can you hear me?
Yes, Hocam, we can hear you.
Can you hear? Yes, we can. Neil, I know one wants to join, but we only got 10. And can he join through YouTube to listen to you?
Yeah, I think he is
because I
listening
have
from
to be
YouTube.
here.
Yes.
Tell him to join through YouTube.
Okay, sure.
On here, we can only be 10. Sorry about that.
No, I think
for
he is
the
there.
system allows only 10 to present.
Okay.
He's in YouTube because he wants to enter. We cannot take him.
Yes,
Okay.
he's in YouTube. Yeah.
Good luck.
Thank you.
Thank you.
Thank you.
Okay.
Thank you.
Now you can share your screen, Ms. Kutlu.
I already shared, but
okay.
Okay.
Yes, it is visible now. Thank you. You can start.
Thank you. So good afternoon, dear professors and all the participants. Today I will make a short presentation about our collaborative work performed by Gregory Brennan and Dr. Owen Tech from University of New Brunswick, Fredericton in Canada. Our study titled The Determination of Critical Height of Unsupported Vertical Cuts Using Experimental and Numerical Methods. So throughout the presentation, the following titles I will try to outline. I will first make a brief introduction to the topic, especially to highlight the importance of the outcomes for practical engineering. Then I would like to give some physical modeling details, explaining the experimental testing program, defining the soil and the testing setup details. And then the numerical analysis part, we have performed the 3D modeling. So I will talk about the 3D model details of the actual experiment. And then finally, the numerical analysis will be evaluated and discussed by comparing with the experimental observations. The safety in trenching and excavation works is the main motivation for this study. So trenching and excavation work is the starting point of most construction projects, were mostly associated with an unsupported cuts. So as we can now follow from the video, this type of work is dangerous, like collapse of even 1.5 meter height of an unsupported cut can kill the field workers due to the great weight of the soil. So according to the American Training Resources reports, more than 100 workers killed in trench accidents each year, in average, which makes like every week 2 workers die in a trench cave-in. So therefore, before we excavate, there is a lot that we need to know, and also there is a lot to estimate about the soil. So on the other hand, if we are being able to excavate without a support, especially in sandy type of soils, this usually means that the soil is in a state of unsaturated condition, where the expected behavior actually can be explained more accurately by the use of unsaturated soil mechanics principles. Then therefore, we can simply say that the stability of cuts is controlled by the metric suction distribution in the field for the unsaturated zone above the groundwater table level. So here the critical height and the stand-up time are the 2 most important factors that need to be considered during an unsupported cut design. Critical height can be estimated using different approaches as analytical estimations, numerical estimations, and experimental validations. In our research, in this research that we are presenting, we use numerical estimations and experimental validation methods and compare the results to see if they do match. So the testing program, first I would like to start. The entire experimental program covers and aims to determine the critical height of an unsupported vertical cut in sandy type of soils for varying water table levels associated with different suction profiles actually occurred. So for this purpose, the studied soil is an industrial sand, referred to as a fine sand. And here in the slide, you can see the basic soil properties and also the grain size distribution curve. To give some more details about the testing setup and the equipments, the experimental testing program had been performed at the University of New Brunswick in Geotechnical lab. The test setup consists of a soil tank, a large-scale soil tank with dimensions of like 1.5 meter by 2.2 meter, and a height of total height of 2.4 meters. And the sand is placed inside the tank by compaction. And then with varying at different water levels, the critical height for the unsupported critical height is determined. But in the context of this paper, only the water level condition located at 0.7 meter depth from the surface is considered. So I'm going to share the experimental results and numerical results only for the groundwater table level that is located at 0.7 meter depth from the tank surface. In order to determine the metric suction variation, high-capacity tensiometers are used, and the measurements indicated that in the unsaturated zone, hydrostatic negative pore water pressure distribution has been maintained. And the next question can be, how did we simulate the excavation? to simulate the vertical excavation, 0.1 meter height retaining panels, as here seen in the figure, the black retaining panels, which each of them has a 0.1 meter height, is used, and they were removed one by one until general shear failure took place. And here at the very end figure, at the very end of the slide, we can see the failure incent, the plan view at the moment of the failure incent is shown here in the figure. In the next slide, I would like to share a video which shows us how the general shear failure took place when the critical height is reached. So as I said, here we only consider a single water level. So in our case, failure took place when we reached the critical height to 0.7 meter, between 0.7 meter to 0.8 meter, when the panel 8 was removed. So the general shear failure looked like this once the critical height is obtained. And then we have our second part of our study as the numerical analysis part. The testing program was also simulated with Plaxis 3D to estimate the critical height. The sand was modeled here as a Moore-Coulomb material with using effective shear strength parameters. And also the Van Ganushen's model is used for SWCC curve, the soil water characteristic curve definition, which fits well with the measured data. And also here in the figure, we can see the Plaxis 3D model, including the geometry, mesh, and boundary conditions for the experimental conditions to simulate the experimental conditions. And of course, in Plaxis 3D, if we consider the unsaturated case, unsaturated condition, the Plaxis 3D contribution of matrix suction on total cohesion is also considered by the model proposed by Vanapali et al. In 1996. This model is also adopted in Plaxis 3D. So here on the left-hand side, we have our variation of the total cohesion variation with depth. So we had the maximum total cohesion obtained at 2.7 kPa, which is 2.7 kPa obtained at 0.25 meters from the test tank. And as we have seen, it reaches to 0 once it is below the groundwater table level. And here also we can see that above the groundwater table level, by the measurements of tensiometer measurements, we just confirm that we can clearly say that there's a hydrostatic pore water pressure distribution, negative pore water pressure distribution. So the numerical analysis results, of course, the stability checks, the stability analysis were performed by using Plaxis 3D model. And during these stability models, excavation was estimated, the stability of the excavation was estimated by calculating the global safety factor using the Fc reduction method. And here the table just shows these details by the depth of excavation. We just simulate the experimental testing setup completely. So step by step, we do a stage analysis. So by removing the panels, we see or we calculated the global safety factors. And here we can see that each excavation, the global safety factors are reduced. And it is dropped to 1.15 after the 7th panel was removed in the model. And removal of the 8th panel caused the failure in the unsupported cut. So this indicates that the critical height is again reached between 0.7 meter and 0.8 meter, as we have it similar in the experimental results. Another two interesting results that we have got and we would like to share with you is that if you look at the results for Plaxis 3D in the plan view, we see that the disturbed soil zone formed an arced shape area indicating the boundary conditions, the boundary effect of the test tank. And also we have attained the failure wedge, which is making an angle of 62 degrees with the horizontal. This is also matches with the slip line angle for the active condition. So to sum up the results and giving the discussions, so we have performed the laboratory tests that was conducted using a large-scale soil tank to investigate the critical height, and also we have performed the numerical modeling analysis using 3D models. And we see that both in the experimental results and in the numerical results, we can get the same height, critical height, which is in between 0.7 meter to 0.8 meter. So this good agreement indicates that the critical height of unsupported vertical cut in unsaturated soils can be reliably estimated through the numerical approaches. So for our next studies or for future studies, of course, the different water levels will also be examined. So thank you very much. I appreciate it.
Thank you, Ms. Kutlu, for this nice presentation.
Thank
we
you.
will be moving to the next presentation.
Okay,
Thank
sure.
you. Have a good day. We have the next speaker, Mr. Yan Liu, I assume is here. Yes, welcome, Mr. Liu. This topic will be again related to rainfall and slope stability. You can share your screen.
Yeah, I'm sharing.
Okay. You are joining us from Japan, right?
Yeah, yes.
Welcome.
Yeah, welcome. Thank you. So sharing, it's shows it's uploading.
Let's see.
Okay,
it's not on the screen yet. It's processing. Okay, let's see.
Okay, maybe.
Yes, now we can see your screen. Thank you. You can start.
Okay, thank you everyone. Very happy to make a presentation in today's conference. And my name is Liu Yan. And today my research topic is risk assessment of slope on the rainfall condition based on model test and motion analysis. And Professor Hazalika is my supervisor. And my research, my presentation includes 6 parts. And the first is the background, and then is the objective. And third part is the methods of my research. And the first part, I will introduce the experiment. And the 5 parts is the motion analysis of my research. And the last is conclusions. And by the climate change, it will cause a lot of rainfall. And the rainfall will introduce a lot of landslide disasters. And the landslide disasters will cause the loss of lives and properties. And the picture shows from the global statistic from 2004 to 2016, there are over 4,000 landslide disasters, and around 75% occurred in Asia. And in Asia, Japan also has a lot of landslide every year. And from the report, shows over 50% risk of landslide disasters in the previous 10 years, and the Kyushu Island is always the most affected one. And this table shows the recent rainfall disasters in Japan, and we can see that every year a lot of people and were affected by the rainfall-induced disasters. And this is 2 cases of rainfall-induced disasters in Kyushu Island for the past 5 years. One is in 2017 and one is in 2020. A lot of people died and still people are missing. So rainfall-induced landslide will cause a lot of problems. So we need to think of a very effective way to reduce these problems. And research will think of 3 methods to evaluate the stability of the slope. One is the numerical simulation, and then is the analytical method. And some research will also conduct a model test to solve such problems. And this is the failure model of the rainfall-induced landslide. We also see that a lot by the analysis of different kind of landslide, we find that there are mainly two kinds of landslide failure. One is a deep failure. It means that the slope will become saturated from the top to the bottom because the rainfall is in infiltration, and so the slip will cross from the saturated to unsaturated part and cause a landslide. And another is some shallow landslide. It will cause landslide from the bottom to the top area because due to the increase of groundwater table. So in Japan, we find that a lot of sandy slope outside, so it is mainly caused by some shallow landslide. So this part of research will focus on some shallow landslide. And so the objective of my research is to identify the main hydrologic behaviors of sandy slope, and we will also evaluate the local safety factor at the different rainfall times and rainfall in groundwater table, and we will also obtain the displacement and flow state on the rainfall. So we will conduct the sandy model test with artificial rainfall, and we will also do the analytical analysis to get the safety factor. So we will also use the software to get the displacement and the velocity of soil within the slope on the rainfall condition. This is a model test. We can see that we have built a model within a box, and we give the rainfall intensity three cases. One is 45 millimeters 1 hour, and 70 millimeters 1 hour, and 100 millimeters 1 hour. And we set the slope angle is 45 degree, and the initial soil moisture content we set is 17%. K7 sand was chosen in this analysis, and we will use the per pressure sensor to measure the pressure at different time, and we use the soil moisture sensor to get the soil moisture content, and we will also use the respiratory pilot camera to get the real-time picture and do the PRV analysis. And this is the local safety factor at different. I don't know why it didn't appear the formula. We just use some formula from the Luning 2004 and 2006 to evaluate the local safety factor at the different area of within the slope, and we will both get the safety factor at the saturated part and the unsaturated part. And for subtle methods, we use the motion analysis. Motion analysis can use to get the displacement of soil, and we can also get the flow state of the slope, and we can also get the soil motion track. And we use PRV to get the soil velocity. This is the principle of the motion analysis. And here I will introduce the result we get from the experiment. We can see that for the sensor, this is the soil moisture sensor, the result from the different rainfall intensity. We can find that whatever the rainfall intensity it is, the soil moisture content will increase due to the rainfall. And S3, it is located at the bottom part, and it is the nearest part, sensor near the slope surface, and it is increased very fast than different other sensors. And once it to reach to the part, it will keep some stable state, and then it will increase again due to all the slope has become saturated. So S3 is the first sensor to increase and re-increase, and S2 it is located at the bottom part. It is the last sensor to find an increase. And this is per pressure content per pressure on the different rainfall intensity. We can find that for the per pressure due to the rainfall intensity, before the groundwater table increase, there is no any diffraction because it keeps zero. And once the groundwater table increase, it will attach some value, and groundwater table increase due to the rainwater infiltrations. And this is a real-time safety factor we got by the analysis. We can also see that because our analysis is focused on some 2D condition, and the 3D condition is also always will be much more bigger than the real time. So our safety factor is a bit slower than the actual result, and we can see that the safety factor we got is S3 is always the farthest part to become less than 1, and S3 the points it's also happen before the landslide happens, so it is practical. And this is motion analysis from our experiment. It records the soil movement and at the 100 millimeters 1 hour. We can see that first is the initial slope, it is intact state. And for the first landslide happened at 59 minutes, the shallow landslide occur at the slope 2. And for the time increase, we can find that the second failure from the bottom of the slope and the last failure landslide, it starts from the top of the slope. And this is from the front view. It because and we can get the same phenomena we can see. This is the PIV result. It recorded the soil flow at the different time. This is the first landslide happen time. We can see that the most of the soil velocity is in the slope 2 area, and this is the second landslide time. We can see that the soil velocity has increased to the middle of the slope, and this last landslide time we can see that the velocity has begun from the top to the bottom. And this is some result we can get from the motion analysis and PIV. We find that stronger rainfall intensity will always cause more effective more effects on the slope. It will result in a faster collapse time. And from the first landslide to the last landslide, the time is very short. It only cost 40 minutes to 24 minutes. So we need to prepare a lot of work before the landslide happens, so protect some lives. And we also find that the rainfall, as the accumulated rainfall of 3 cases all beyond 100 millimeters at the last landslide time. So this is my conclusions. We can see that the soil moisture will increase due to the rainfall infiltration, and it will keep some stable state for a short time, and then it will re-increase due to the groundwater table increase. And our analytical method result shows that it is a real-time safety factor of the unsaturated slope. It can be used as an early warning signal of the work. And the motion analysis and PIV also provided the information of displacement and velocity. And we can see easily that the greater rainfall intensity will cause the earlier rainfall landslide and greater rainfall damage. That's all for my research. Thank you.
Thank you, Mr. Liu, for your nice presentation. I was wondering, not about your presentation, but are there any early warning systems in Japan? Are you aware of any early warning system for?
Yes. We are also, our group also focus on the early warning system based on IoT. We use different sensors and different some microcomputer, some Raspberry Pi, and connect with different sensors and put it outside with Wi-Fi, with some LPWA, different data transmission. We also focus on this area. This is a very small early warning system. Yeah.
Okay, very good. Thank you for your presentation.
Thank you.
We go to the next speaker in the session. This will be about GIS susceptibility maps for shallow landslides from Canada, case study in Canada. Michael Barbosu, Professor Barbosu, welcome. You can share your screen.
Hi, Nijan.
Hi.
And I want to thank you, and thank you, Professor Kavita Atalar, for all the work he did. Here is my screen now. Okay. Let me see. Well,
Is it working, the share button?
Yes. It's just uploading.
Okay, maybe it takes some time.
Something, yeah. If not, I've sent the file anyways.
Okay, let's just see if it can upload.
Okay, so trying to share the screen.
Okay.
Can you see my screen?
Right now I don't see, but let's wait. If it's uploading something. It's not visible yet. Does it say something on the screen or? Ah, yes, now it appeared.
Okay.
Okay, great.
Yeah.
You can start. Thank you.
Thank you. So this is a work we've started with several collaborators, and I'm presenting it with Dr. James Green from University of Montreal. The project has been going for over 10 years now. And could you go to the next slide, please? Okay. We've started this project because landslides on various scales represent a very important category of morphological processes in Quebec, and they cause instability problems for infrastructures, and unfortunately, we also had loss of lives. A little bit of the background: the lowland areas of Quebec were covered at the end of the last glacial period by sensitive marine clays. And these have been created by preconditions for large deep-seated landslides. However, for shallow landslides, for superficial landslides, there are other factors that need to be taken into account. And in this paper, this is what we'll do. We analyze potential for shallow landslides, and we focused on an area that will be shown on the next slide, La Bissonnière Amphitheatre near Shawinigan in Quebec. So here is on the left the map of Canada, and then you can see here Shawinigan, Quebec, and the larger map of our area of study area in La Bissonnière. The next slide, please. So in Quebec, there are four major categories of landslides. The rotational landslides, where the fracture plane corresponds to an arc of a circle, and the movement of material occurs in rotation, having a deeper fracture surface and debris volume. The retrogressive landslides, which are pretty much like the rotational landslides, except that there is a succession of ruptures. And then we have clay flows characterized by very strong retrogression and major liquefaction of the clays. And then we have these shallow landslides, which we're interested in. They can be up to 2 or 4 meter deep in developing marine sediments, and they occur in large numbers every year. These landslides are a consequence of different factors, and of course, the main thing to consider is the change in the stress of the slope. And these also represent a preliminary step for progressive failures, which can develop into large-scale mass movements. And for this project, on the next slide, please. The methodology that we used was based on the factor of safety, and we generated some susceptibility maps to shallow landslides using the infinite slope models with a spatial evaluation of the factor of safety given by this ratio, very well known formula, maybe not under these parameters, but nevertheless is the same. We have the two forces acting on the slope, the frictional and the resistance one. And here are the parameters that we took into account: cohesion of material, density, pressure water, slope angle, of course, thickness, angle of internal friction, gravitational acceleration. And I would like to insist on the last parameter, this m, which for m equals 0 represents the fact that the water table is at or below the slide surface, whereas for m equals 1, these are the limit scenarios. The water table is at the ground surface. So for these two values, m equals 0 and m equals 1, as you will see in another slide, we generated the susceptibility maps. Could we see the next slide, please? So for preparing these maps, although in theory we have Fs equals 1 to be the limit for stability and instability, in practice 1.5 is accepted. We considered 6 classes of susceptibility, from high susceptibility to stable areas, and these corresponding to the values of the factor of safety, Fs. In generating the maps, we used ArcGIS with a spatial analyst, raster calculator, and we followed these steps. The first one was generating the dam, then TIN was converted to a raster format. Then in the field, we had 45 points where we collected areas. In these areas, we had soil analysis. We performed for all these 45 points where we had these samples. And we determined the angle of internal friction, cohesion of material, density of materials. For points where we didn't have values for these parameters, we interpolated or extrapolated the values determined by these 45 points. Finally, Fs was fed into the raster calculator, and we generated the susceptibility maps that are on the next slide. So here are our final comments and our final result. The final result is the map to the left, which is mostly blue, with the water table at or below the slide surface, and then m equals 1, water table at the ground surface with mostly red. So here the differences depending on the water table, and on the next slide will lead to the conclusions. I try to keep it short, the presentation. So the next slide, please. So from the two maps, we see that most regions in our study area in the La Bissonnière amphitheater are relatively stable. In percentages, this translated to areas from 6% when m equals 0 to 35% when m equals 1. These were the zones affected by that could be affected by shallow landslides. So zones susceptible to shallow landslides vary from 6% to 35%. As expected, most zones that are susceptible to shallow landslides are also zones where we have steep slopes, but we can also identify in the north and northeast part some areas where there might be shallow landslides, and that is especially due to the cohesion of materials and higher content of clays. We also noticed some shallow landslides that occurred in areas with direct or indirect anthropogenic impacts, and that is very important. Therefore, especially in the current of the context of climate change, the whole issue of risk assessment and susceptibility to landslides, we believe, should be monitored and constantly reassessed. We checked and confirmed the validity of our model. As I said, we've studied the project 10 years ago for comparisons with all the photos and recurrent field observations. And in fact, one of the latest landslide that occurred in Shawinigan, affecting 4 houses, luckily no lives were affected, occurred on October 24th, 2021. So these are our conclusions. As I said, I try to keep it short in the interest of time for everyone. I just want to acknowledge and extend our special thanks to 2 other collaborators, Professor Alexandru Imbran and researcher Corina Nikoric. They have helped us all along during this project. And the last slide, please. Thank you. And if you have any questions, you have my email address there, and I would be happy to answer any questions you might have.
Thank you, Professor Barroso. Very nice presentation.
Thank you.
Professor Atalar, do you have any comments or you want to say something? You are muted, I guess.
Yeah,
okay.
That's okay. We can go to the next.
Thank you, Professor Barroso. Now we will go to the next presentation.
Thank you, Mijan.
Thank you. Have a good day. Now the next presentation, I think the authors are not here, but just I will read the paper's name. Slope Stability Analysis of Open Pit Mines Using Statistical Methods by Petra Ola and Peter Görög, but they are not able to join, I assume. So we will be moving to the next presentation, which is by Professor Salih Saner from Northern Cyprus. This is about a special statue in Northern Cyprus. Buyurun hocam, please.
I am clicking on, but it, okay.
Yes, okay, it works.
Okay.
Thank
Hello, everybody. I am joining from Northern Cyprus. We couldn't manage to bring you all here, but now I am bringing a case study to your attention from Cyprus. There is a monument on the northern coast of Cyprus, and it has some devastations, depreciations. Some movements can be seen in the ground. And also, municipality is planning to build recreation facilities in the area. But the area is the area suitable for constructions, or what kind of precautions should be taken. This is the monument, and I'm going to show a couple of photographs also showing small movements. Talk about geomorphology, geology, mass movements, causes of mobility, conclusions, and finish my talk. This is the area again from another view. This is the monument here, and it's the beach area. It is about 7 kilometers from the city center of Girne. Here, this is beach today, a private beach, and continuation of it is going to be a municipality recreation area and beach facilities. As you see, there is the plateau area here and slope. So we wanted to study the suitability for ground movements. Is it going to be a landslide area or what? Causes of mass movements, as we know, steep slope, soil and rock properties, bedding of the formations, the post-angle unconsolidated material, groundwater, vegetation, earthquake, and volcano in the area. First, we started with checking there is a river, not river, a small creek, bringing some water. This is the coast area. a river is coming to the area. According to our estimation, 960,000 tons of rain is receiving, this drainage area is receiving, and 320,000 tons, they are just estimating 1/3, is flowing to the sea through this creek. And our statue is here. So the water, and the water also, there is a shallow water aquifer, which is not a big aquifer, but seeping continuously in the area. And at the mouth of this river, only the mouth of this river, nowhere else. In the shore, we are having gravels. From where is this one coming? We don't have it anywhere else. Then we found it in a outcrop of, a mass flow, mud flow, or whatever, debris flow. So this debris flow is, and also the river is bringing time to time when we have flooding. So it means this river is sometimes with the rains, it may bring material, or it may have mass movements bringing something. We said we need to know the geology, the coastal area. This is the material brought by river, and on the top, this yellow area, I don't know whether my cursor is seen there. The yellow area is a limestone, young limestone. This is a shale slope area, shale, flysch formation, and dipping towards sea. And this one is a horizontal limestone. It is very young, about, let's say, 1 or 2 million years old, horizontal laying, and forming a plateau in the area. And you see there's the plateau. This is not exactly from the side. Little bit, 1 kilometer away I went to check this photograph. The plateau and making a scarp, but here we don't see the slope because shale is starting at the sea level. At the edges of the plateau, there are scarps and some, always this kind of fractures, which are gravity fractures, are possible. In the site, here's the monument at the northern corner monument. You see the monument, and you see some limestone blocks there, because what they did when they were constructing this monument, they pushed the rocks down, opened a flat area for opening ditches for foundation, and removed it. Actually, this was a strong cap on the shale. They made a good engineering, and they put the statue on shale. This is how the shale outcrops are seen in the area, very thin bedded. When you take it in your mouth, this one, chew it, it is like a chocolate. There is no coarse in it. Taste is not like chocolate, but the chewing is very soft. And I took 2 samples. I put them in a beaker. In half an hour, this is a rock. In half an hour, it became mud. So it disintegrates with water. And the surface always is soil formed from alteration of these shale layers. There is no thick sandstone to give it strength. Therefore, some movements can be seen in the area. You see blocks placed around the statue moved. buckling of the retaining wall, and on the floor of the statue there are cracks, and this is the foundation that fracture occurred in the foundation. There are this kind of things, always showing us some movements, instability, or there is no big movement, but these are indications for the future. This is possibility. We have to consider the ground structure, ground geology. In petroleum industry, 30 years ago, they came up with a sentence always. They are saying, do not do it without GNG. People nowadays are going with computers, modeling. Yes, we have to model, but your model should depend based on correct geology first. Correct geology. Don't do it without GNG, without geology and geophysics. At that time, it will be correct. Here, as I told, the limestone forming a plateau is a strong rock. It is about 20 meters thick in the south, and this one is shale. The beddings are real beddings, this way. Sea is here, coast is here. So bedding is in this way. And what you see on the surface, sometimes we may find the odd outcrop of this one, but usually surface is coated with soil formed from alteration of the shale. So shale soil, I thought this one. Soil formed from shale. And it is time to time sliding. The material here, this scarp, when it is broken, either it rolls down or it rolls somewhere and gradually it slides. And maybe soil is covering it. When you drill a well to investigate the ground, you may find a soil, a shale, rock, and underneath another shale. So this may be, so you can put layers here mistakenly, but there is no any other limestone in this sequence. It is pure shale. And today, in order to build, this is the slope is about 15 degrees, and these are 30 degrees, this bedding inclination dips, 30 degrees. If you make a cut here for construction, you are, equilibrium for the forces will be changing. You may get, you are igniting, or you are stimulating the instability of the ground in this case. You have to be very careful. So what we are saying, no big damage observed. There are some damage. Geological structure and bedding properties of shale unit is indicating a risky ground for construction. Shale slope should not be disturbed, we are saying. Shale slope should not be disturbed because the alteration that is making shale soil is protecting the real outcrop from water. Because as I said, water, the rock is getting disintegrated in water. We have to improve vegetation in the area. And no, there was one more thing. The limestone forming the plateau should not be removed in the area. This model, this geological model that we made this study in the area, we observed it in exactly the same in 100 kilometers distance along the North Shore. So what I mean, in Girne or in other village or in 100 kilometers length distance, the problem is same. This is all what I wanted to tell you today. Thank you very much.
Thank you, Professor Saner, for your nice presentation. Actually, I have also visited this site. I have observed the ground deformations, so very coincidence to see your presentation today. And also, I have tried to put another shale piece from Turkey in water, and similar to your figure, it gets disaggregated in water in a very short time. So very nice to see your similar approach here.
In 30 minutes, what is separated. In 30 minutes, of course, it depends on what type of clay minerals it has, and absence of sandstone layers in between. This shale is massive shale.
Yes, it's probably interesting for this statue site. What is the depth of failure zone? It could be interesting to observe or measure by inclinometers.
We would like somebody to do modeling based on this geology.
Thank you very much for your presentation.
Thank you.
We will be going to the next speaker. This topic is dynamic response analysis of highway embankments. It will be presented by Mr. Yasin Toksoy and written together with Professor Ayşe Edinçliler.
Yes.
Yes, Mr. Toksoy, let's share your screen.
Can you see now?
Yes, we can see. And you are joining from Istanbul, is that right?
Yeah, that's right, yes.
Okay, thank you for your joining.
Yeah.
Okay, you can start, thank you.
Yeah, thank you. Welcome all. My name is Yasin Sayit Toksoy. I'm a PhD candidate from Boğaziçi University, Kandilli Observatory and Earthquake Research Institute. And my presentation is about dynamic response analysis of highway embankments. My presentation starts with an introduction part where I'm going to give you some brief information about the seismic performance of highway embankments and the geosynthetics. And then I will continue my presentation with the determination of the foundation soil parameters that I used in my numerical analysis by pressure meter tests, multi-channel analysis of surface waves, electrical resistance tomography tests, market tremor measurements, and field vibration tests. And then I will give you detailed information about the finite element analysis of highway embankment models and the related numerical results. As you all know, highway embankments are essential lifelines that must be in continuous operation even after the natural disasters such as earthquakes. But unfortunately, there are numerous cases of highways exposed to earthquake-induced damages from minor to severe scale. That's why the seismic performance of these structures should be improved, especially in seismic regions such as Turkey. In light of the recent advances and the latest research, geosynthetics can successfully and be effectively used to reinforce highway embankments against the primary and the secondary effects of the earthquake-induced damages. So reinforcing these highway embankments with geosynthetics is a globally accepted technique for static conditions, we know that, but it is a novel approach to use them for the mitigation of earthquake hazards. It is important to estimate the approximate dynamic behavior of these kind of engineered structures via numerical simulations before the experimental studies. This study covers the numerical modeling of a dynamic response of full-scale highway embankment models using the mobile seismic shaker in the field as a dynamic source. So this numerical simulation phase has been used to ensure the true structural design and the true instrumentation in the field. The numerical simulations have been performed implementing the finite element modeling technique using the Plexus 2D software and includes the dynamic response analysis of dimensionally identical unreinforced and geogrid reinforced highway embankment models. Here in the picture you can see the test area I'm talking about. So this numerical study, as I mentioned, is a simulation of the field scale testing in which the input parameters here are based on the previously performed geophysical tests. The foundation soil parameters here for the numerical analysis were precisely determined by performing the pressure meter tests, MASW tests, 3D ERT tests, microthermal tests, and field vibration tests. First of all, we performed pressure meter tests in the proposed test area to obtain the elastic modulus profile of the test area. As you all know, this parameter is crucial because of the calibration of the numerical models. After that, we performed MASW tests in 8 profiles, as you can see in these lines above in my defined area. So for each and every 8 profiles, we determined these shear wave velocity profiles up to 30 meters of depth, and used also this for the calibration of the models and also the selection of the proper location of the embankment models in the test area. The another geophysical test we performed is 3D electrical resistivity tomography tests. This is one of the oldest and the most commonly used geophysical exploration methods. And it is a very useful method for characterizing the subsurface materials in terms of their electrical properties. This field test setup requires the deployment of an array of regularly spaced electrodes like this. We have 86 of them in this example, and they are connected to a central control unit via multi-core cables. This is a very useful method, especially to monitor the subsurface conditions, to any discontinuity, any faults, any sinkholes. It's a very useful one. And those are the results obtained from the ERT tests. In addition to the 3D one, you may also have the section views, as you can see. And once you obtain the shear wave velocity profile of the test area, this resistivity can also be easily correlated with the MASW tests. So you have a clear understanding what is under surface. You have a clear view here. And we also performed the microthermal tests. This is a low amplitude ambient vibration of the ground caused by man-made or atmospheric disturbances. Observation of these tests give us useful information on the dynamic properties of the test site, such as the predominant period and the amplitude. And it is also commonly used for microzonation studies. In this study, we performed 3 microthermal readings for 1 hour each and using 3 different seismometers. And we obtained the site characteristics for 3 M sites. We obtained the natural frequencies, predominant periods, and H/V ratios. In addition to all of this, we also performed field vibration tests. To investigate the wave propagation properties in the test area, we placed a series of 12 geophones in a line of series and used the mobile seismic shaker owned by our department and used it as a dynamic source. And we have many different parameters, like 50 case parametric set. And now I'd like to mention the finite element analysis of my highway embankment models. As I mentioned, the numerical analysis were performed using the Plaxis 2D Connect Edition software. As the embankment models are symmetric, only the right half here has been modeled and subject to the dynamic excitations. Here you can see the dimensioning also. As you all know, when we perform dynamic response analysis in this finite element analysis modeling method, you have to define special boundary conditions to avoid distortions and not to get the unrealistic results. That's why viscous boundaries are defined at the edges of the meshes. And then the model design and the highway embankment material selection here were carefully defined to meet both the 1993 H2 and the 2013 KGM technical regulations at the same time. So these thicknesses of the asphalt concrete layer and the granular aggregate base layer were defined as 15 and 30 centimeters respectively for all cases to meet those regulations at the same time. Those are the material models here, as you can see. The material properties of each element here were carefully selected in accordance with the current regulation and the latest literature. The foundation soil parameters, however, were previously determined by the performed field tests and the geophysical experiments that I mentioned a few minutes ago. We used geogrid reinforcement in one of our models, And this is a biaxial one and has an ultimate tensile strength of 40 kilonewtons per square meters, and it meets the FHWA regulations. Here you can see my dynamic input motion. It is 0 to 30 Hertz sinusoidal motion with a peak amplitude of around 1 G. We selected this one because this is also going to be used in the field experiments as well. This is what our mobile seismic shaker can also apply. As this is a parametric study, we have like a 50 case here. This is just a selected example input motion. And those are the results obtained from my unreinforced model, as you can see. This is the total displacement distributions for the unreinforced embankment model. As you can see, the total displacement value is around 15 centimeters, and the displacements are concentrated at the crest level. This is a crucial area for the highway embankments. And this is the transmitted accelerations chart, as you can see. Keep in mind that the input dynamic motion has the peak ground text PGA value of like around 1 G. However, it's amplified to around 3.9 G, around the crest level at the top of the embankment model. But when we apply 2 layers of geogrids here, when we integrated here one layer at the bottom of one and another one at the middle height, the total displacements are decreased to around 11 centimeters. The displacements are also concentrated at the crest level. And also the accelerations here are attenuated from 1 G to 0.85 G. As you can see, also the transmitted accelerations are concentrated around the geogrid reinforced zone, not at the crest level. So to sum up my numerical results. Performed dynamic response analysis of the proposed embankment models here revealed that the geogrid reinforcement can substantially and successfully reduce the total displacements and the transmitted accelerations at crest level, and these are the key structural performance indicators. With the help of this geogrid reinforcement, it provides the additional tensile strength. That's why the total displacement here around 20% less in the geogrid reinforced one when compared to the unreinforced one. And by means of total accelerations, geogrid reinforcement can successfully absorb the dynamic energy and transfer less dynamic motion to the embankment structures. So obtained results by means of maximum accelerations are around 78% less in geogrid reinforced model than when compared to the unreinforced one. So these results highlights that the geogrid reinforcement is an effective reinforcement element to mitigate the earthquake hazards of higher embankment models. And we would like to thank our Boğaziçi University Research Fund with the given grant number for supporting us, for supporting this study. Thank you all for listening to me.
Thank you, Mr. Toksoy. Very nice presentation. I was wondering if you defined any interface boundary at the geogrid soil interface. And normally these geogrids will interlock with the underlying above-lying materials. I was wondering if you considered any kind of a special interface or just no special boundary.
In the literature, yeah, like 15% in interfaces, 15%. How to say? Not rigid. It is okay. It is not one point. It's not rigid, but 85% rigid. Let's say yes. That's how I defined my interfaces. Okay. Between the soil and the geogrid reinforcement, as suggested in the literature. Yeah.
Okay. And one little question also: the displacements you were mentioning, are they horizontal or vertical or combined?
The dynamic motion.
Yeah, the displacements you were 15 centimeter and 11.
These are total.
It's total. Okay.
Yes, it's total.
Total displacement. All right. Thank you very much.
Thank you.
We will go to the next presentation. Next presentation is going to be presented by Peter Rogenbuke, if I pronounce correctly. And after that, we found the video of the previous presentation who were not able to attend. Petra Ola sent us a video. So after the next speaker, we will see the video after Mr. Peter's presentation. All right.
Nejan, can you hear me?
Yes, hocam.
Since we are all here except Petra, because Salih Hoca wasn't here, can we take another picture because until Peter prepares all of us on the show? Can we get it from the technical?
Okay, sure. Okay.
Hepimizi koyabilir misiniz? Şimdi bir fotoğraf alalım çünkü alamadık daha önce lütfen.
We will be taking a group picture. Okay. Thank you. I will now take a picture. Thank you. I got it, hocam. If you want, I will send you these pictures.
Okay, thank you very much. Okay, go ahead.
Thank you
very much.
Thank you.
Now we will listen Mr. Peter's presentation.
Okay. I'll try to share. Just a minute. Okay, can you see?
Yes.
Okay. So hello everyone, I'm Peter, and today I'll be representing our findings on this study called Experimental Investigation and Visualization of Failure Surfaces in Pipe Soil Interaction Problems using PIV technique. So let's start with the introduction. As we all know, in today's world, buried pipelines have great importance in transportation of fluids, such as sewage systems or maybe fuel systems. And one of the most common material is PVC pipes, since they are cost-effective and also they're competitive against other materials such as steel. And the analysis of these systems can be considered as a soil structure interaction problem. And when we looked at the literature, we saw that the soil structure interaction problem is mainly investigated in terms of bearing capacity and load displacement curves. So what we did is we investigated the effect of relative density on bearing capacity when there's a pipe below the foundation, and also we included the image analysis to previous techniques. So this is our experimental setup. So as you can see, we have a loading system which contains our load cell. We have a strip footing, model footing. We have the pipe beneath the foundation. This is our test box to fill the sand. We have camera to capture photos for image analysis, and also we have the loading frame to put the system on. So tests were carried out in a rigid box filled with sand at the target relative density. The system has a width of 100 centimeters, length of 60, and also a height of 50 centimeters. Then model footing has dimensions of 10 centimeters width, 50 centimeters length, and 3 centimeters thickness. And those loads and displacement were measured by using load cells and an LVDT transducer. Following that, throughout the experiments, we used in total of 3 different load cells with 3 different capacities ranging from 500 kilograms to 2 tons. And our LVDT stroke length was 150 millimeters. Other than that, measured values were recorded using data loggers, and we were able to keep the loading rate at a constant at 10 millimeters per minute. So we took photos for image analysis at every 2 millimeter or every 12 seconds if we convert it like that. And our failure criterion was chosen as the displacement at 10% of the foundation width, which corresponds to 10 millimeters, since our foundation width is 10 centimeters. So 1 centimeter settlement is our failure. So for image analysis, we used particle image velocimetry, which is called PIV. It's a novel image analysis technique used in many engineering applications, and it can be modified for the geotechnical engineering applications as well. We use the MATLAB-based GeoPIV RG software, and what this software does is it divides the region of interest into meshes, user-defined meshes, and calculates distances between consecutive images and the reference image for each mesh. And by plotting the results as in surface contours, we can observe the failure surfaces or influence zones or displacement fields, whatever you want to call it. Then we have our soil properties. We obtain our sand from Çerkezköy region of Istanbul, Turkey, and it is classified as poorly graded. During relative density calculations, we used specific gravity maximum minimum void ratios. And then we have our experimental method part. In total, we conducted 6 experiments for this case, for this study. 3 of them with buried pipe and 3 of them were without the pipe. We also used 3 different relative density values to see the effect of it, ranging from 35% to 65%. So as you can see, h is we use normalized parameters. So h is the vertical distance between the bottom of the foundation and the crest of the pipe. D is the constant pipe parameter, diameter. Our pipe was 75 millimeters in diameters. B is the foundation width. As mentioned, it is 100 millimeters. And Q is the applied load. So for the buried pipe, we considered only H over D, which is the embedment ratio, equals to 1. So the H, since D is equal to 75 millimeters, the distance between crest and the pipe is 75 millimeters. And desired relative density was established by calculating the necessary soil mass for all of the bugs, all of the rigid bugs, using index values. Then we place the soil in 10 layers, each layer corresponding to 1/10 of the total mass and of the total volume. Then we have our results. So we first start with PIV results. As you can see from the figures, resultant contours at 10 millimeter displacements, when we look at higher relative density or lower, higher, as relative density gets higher, we see that the displacement field below the foundation becomes narrower. And for the pipe case, with lower relative density, we see a higher displacement field just below the pipe, as you can see these lighted regions. And lower relative density leads to a wider displacement field just above the pipe, crest of the pipe. And we have our stress displacement results. As expected, highest relative density gives us the highest load carrying capacity. But when we compare it, in both cases, we get highest carrying capacity in 65% relative density. But for the case with pipe, load carrying capacity drops to around 70% for 35% and 65% relative densities. But when we look at the 50% relative density, it drops only to 90% of the case without the pipe. As you can see from the differences, there's a less drop in 50% relative density. Then we have our conclusions. So in this study, we tried to examine or investigate the soil pipe foundation system by measuring base pressure and displacement acting on the model foundation. And we tried to visualize it, the deformation of the soil stratum using GeoPIV-RG analysis. This program managed to envision the deformation zones of different relative densities, and it's a valuable tool in visualizing the deformation zones with the pipe. Since pipe leads to a different separate deformation field in sense of different relative densities. And further investigations or studies could investigate the effect of geosynthetic or geogrades, for example, georeinforcements, on deformation field and bearing capacity, and they can be combined with, again, GeoPIV analysis. And also for different soil types, it can be examined using the strain contours which GeoPIV can provide. So we thank TÜBİTAK for funding our project, and that was my presentation. Thank you for listening.
Thank you, Mr. Peter. Very nice work. We will be, to save time, we will be going to the next presentation. Thank you for your work. Final presentation will be by a video recorded by Petra Ola on slope stability analysis of open pit mines using statistical methods. If the video is ready, we can take the video. Then we will be closing the session. Okay.
Welcome to the audience. My name is Petra Ola. I am from Hungary. I am a PhD student from the Budapest University of Technology and Economics, from the Faculty of Civil Engineering, from the Department of Engineering, Geology and Geotechnics. It's a pleasure to me that I can give you a presentation about my study in this conference. I hope you will enjoy my presentation. Now I share my screen. So my presentation is about the slope stability analysis of an open-cast lignite mine, and I also would like to introduce a case study in which I show the comparison between two different slope stability calculation methods, the deterministic and the probability-based. So first of all, I would like to talk about the differences between these methods. Then I will show you how we can consider the uncertainties during the calculation. Then comes the steps and the most important factors of the probabilistic slope stability analysis. And finally, I will show you an exact lignite mine, which was my diploma work and also my research topic now. Slope engineering is perhaps that geotechnical subject where most uncertainties dominate. For example, geological anomalies, the variability of soil properties, lack of enough data, changing environmental conditions, unexpected failure mechanisms, simplifications and human mistakes in design and also in construction phase are all factors contributing to uncertainty. Probabilistic slope stability analysis, or in short the PSSA, was first introduced in slope engineering in the 1920s. In the deterministic calculation, a single unique value is defined to each input parameters, while on a probabilistic basis, the input parameters include a whole range. The deterministic method doesn't take into account the uncertainty. It relies on constant values, so it runs only one calculation and examines only one combination, and the result is also a single value, namely the factor of safety, or in short, the Fs. While the probabilistic method takes it into account the uncertainty by interpreting distribution functions to statistical variables. It runs hundreds or thousands different combinations of parameters, and the result is a distribution function of the Fs's, in which we can conclude to the probability of failure, or in short, the PF. When it comes to calculate in a probability-based method, we need to enter the input parameters correctly. It starts with the analyzing of a large enough data set, and it is very important that we have to have large enough data set. Then comes the determination of the most fitting distribution type with the method called goodness of fit. After that, we need to determine the statistical parameters such as the mean, the standard deviation based on the type of the distribution function, and the relative minimum and the relative maximum values. While the PSSA is a very nice concept, we should consider the following weaknesses. The stochastic distribution uncertainty, because the PF is greatly influenced by the choice of a probability distribution selected for the input parameters. The multiplication of uncertainties. The more data we can use, the more accurate PF we can get. The parameter correlation uncertainty, because the PF is strongly influenced by the correlation between the random variables. The highest PF failure surface vs the lowest FS failure surface. Because Oka and Wu said that the failure surface with the minimum factor of safety doesn't necessarily have to be the failure surface with the maximum probability of failure. So therefore, it is not necessary to consider all failure surfaces in a probabilistic computation, not just with the minimum Fs surface. Lack of time dependency, because the computed PF doesn't have a time scale. And finally, the lack of the uniform standard for the acceptance of the maximum value of the PF. So in one word, we can see there are also uncertainties in the PSSA too. Now I would like to present my own calculations on the slopes of the Visonta lignite mine. Visonta is located at the northeast region of Hungary, where open-cast lignite mine has been extracting since the 1970s. On the examined mine, named the Easter number 3, it is required to design high slopes and ensure their stability before mining began and also at the end of the mining process. The slope stability calculation started in a deterministic way, and then I checked the stability of the optimized sections on a statistical basis. Lignite is the youngest coal with a strongly woody structure. It has a relatively low calorific value, but in Hungary they use lignite to generate electricity. Lignite can be found in large quantities under thin cover layers, but it can be easily extracted, and we can say that it also stops vertically. Out of 2,693 samples, I got 81 relevant, and out of 16 different soil layers, I could give statistical parameters for only 7. The random variables were the shear strength parameters, so the cohesion and the internal friction angle. The chosen method was the Latin hypercube method. This table shows those layers which had enough data to a statistical analysis. You can see their statistical values and the chosen distribution type here. There were 6 sections calculated: the first, the third, and the fifth on the south, and the number 21, 24, and 27 on the north side of the end slope. The most exciting results came out of the section 24, so I would like to introduce it to you. I started the calculations with the deterministic method. After optimizing, I got that the lowest failure circle has above 1.5 Fs, so according to the Eurocode, it is safe. Then came the probabilistic calculation on the same section with the same geometry, but with the statistical variables. In the case of the section 24, I got that the Fs deterministic is above 1.5, it is OK, but the Fs mean, which is the average of the 1000 runs, is much less, it is under 1.3. But the PF is relatively high as well, it is almost 13%. You can see the same result in a histogram of the section 24. Those runs where the Fs did not reach the 1 are highlighted in orange. Here you can see the distribution function of the sample's run. The inflection point gives the mean of the factor of safety values. This graph shows that as the number of samples increases, the curve converges to a constant value. The worst possible combination of the input parameters is at run number 177, when the probability of slope failure is above 14%. You can see all the 6 section results here. We can say that the mean Fs were lower than the deterministic in every sections. And after all, the question arises, what is the maximum PF that can be considered acceptable in a slope design? According to the literature, we have certain tables that we can use to answer this question. For example, according to Sjöberg, slopes can be grouped according to the severity of the consequence after failure. It shows that the consequence of failure is related to the probability of failure and the reliability index. Schellmann, on the other hand, said that we should consider the mass involved in the failure. And Veselo and Reed defined the design criteria for the slope size and also for the consequence of failure. But there is another method which is called the Fspf selection matrix method, in which after 5 certain steps we can choose the minimum value of factor of safety and the maximum value of probability of failure according to the examined unique slope. There is a huge table from which we can select the minimum Fs and the maximum Pf for each slopes. For example, for a mine like Visonta, it is required to get a Pf under 5%. To sum up, uncertainty should never be ignored in slope stability analysis. When we design slopes in a deterministic way, we usually complete the design when we reach 1.35 value of Fs. But in the case study, we saw that there could be combinations during the probabilistic calculations where the slope could fail. After all, in my opinion, we need to try to reach the 0% of probability of failure as close as possible. Thank you for your attention. If you have any question, please feel free to contact me via this email address. Thank you again and goodbye.
We thank Petra Ola for sending us the video of her presentation. Interesting talk. Now we will be closing this session. Thank you everyone for the presentations. They were interesting topics. And thank you all the attendees for their interest. Professor Atalar, if you have anything to add.
Yes, I have something to say. I would like to thank you all. You did a very good job. Thank you very much. Thank you very much.
Thank you to all presenters, yes. Okay, so then the next session will begin in a few minutes, I assume. Enjoy the rest of the conference.
Yes,
everyone.
It's beginning soon, yes.
Soon, okay.
We gave them the notification. Okay.
Okay, okay.
Thank you again.
Bye-bye, everyone. See you.
Bye-bye.
I'm catching a bus, never nothing when it's really down.